Hello and welcome. In this workshop, we will learn how to create a CFD-ready mesh for simulating the flow of air around an axial fan using the Ansys Fluent meshing watertight geometry workflow. We will specifically look at how to assign periodic boundaries and how to prepare the CAD to facilitate the creation of these periodic boundaries. Without further ado, let's get started. Let's first look at how to prepare the CAD in Ansys SpaceClaim. Launch Ansys SpaceClaim and load the provided CAD file. The model we have here is that of an axial fan placed inside an enclosure. A separate fluid region is created around the fan to facilitate the implementation of the MRF approach while running the simulation. The enclosure and the MRF region are considered as the fluid regions. The fan geometry will not be required for the simulation and is subtracted from the MRF region. The fan shaped cutout in the MRF region will be considered as a no-slip wall during the simulation. Because of evenly spaced nature of the blades along the circumference of the hub, only a quarter of the geometry is sufficient to represent the entire geometry while using the periodic conditions. We will now split the geometry into 4 equal sectors with the help of the planes and consider only the one sector which will be transferred to the Fluent meshing. Body labels have already been created for the enclosure and the MRF region. Go to the Groups tab, select the two labels, right-click and select Hide. This will hide all the surfaces in the model except the surface of the fan. Align the view with respect to the x-axis. To create planes, click on the plane icon in the ribbon of the Design tab and then click on any reference edge or surface to create and align the plane. For this demo, let's use the edges on the hub as a reference. Make sure all the surfaces are unhidden from the graphics window. As the fan geometry is not required for the simulation, let's hide and suppress it from the physics. Now, to split the geometry, select the split body operation from the ribbon, select the target objects, that is the MRF and the enclosure regions, by simply dragging the selection box over it. Now, select the cutters, that is the two planes. Click on any one of the planes and while pressing the control button, select the second plane. Now select the sectors to remove by clicking on them. We are now left with just one sector of the original geometry. Before saving the file, there are few requirements to be fulfilled in order to successfully set up periodic boundaries during the meshing phase. Firstly, ensure that the surface areas of the opposite sides of the sector are equal. Unequal areas is an indication of unequal split of the geometry. Use the Measure tool from the Measure tab to compare the surface areas of the sides. In our case, the surface areas are equal and hence we are good to go. Secondly, in models with multiple regions that are aligned and have the same periodicity as it is in our case, it is important to consider that only one set of periodic boundaries is supported when using the watertight workflow. Hence, it is required to group all the periodic faces on each side under a common named selection. Let's assign side 1 named selection to the faces on this side and side 2 named selection to the faces on the other side. In addition, it is also necessary to perform share topology at the CAD level. To do that, click on the share operation in the ribbon of the Workbench tab. The tool will automatically detect the coincident faces and edges. Click on the green tick mark to execute the task. The CAD model is now ready to be transferred to the Ansys Fluent meshing. Let's now switch to Ansys Fluent. Here is Ansys Fluent launched in meshing mode with the watertight geometry workflow selected. Keep the default settings and load the CAD file in the import geometry task. As the geometrical features on the fan boundary zone are relatively small, we will add local sizing controls to ensure that these features are accurately resolved. In the Add Local Sizing task, set the size control type to face size option and the target mesh size as 1 mm. Select the fan zone from the list of labels and execute the task. Next, in the Generate the Surface Mesh task, set the minimum and maximum size as 3 mm and 15 mm respectively and increase the cells per gap to 2. Execute the task with the rest of the inputs at default settings. Once the surface mesh is generated, the user is presented with a warning to improve the surface mesh quality. This is because the meshing algorithm detects cells that have a skewness value greater than 0.9, which is generally not recommended. However, the number of bad quality cells is only 1 and the average skewness of the associated region is very low, indicating an otherwise high quality mesh. For these reasons, we will ignore the warning and proceed without performing any surface mesh improvement operations. As we will see later, this bad quality cell is automatically corrected in the process of creating the volume mesh. Once the surface mesh is ready, it's time to add an additional task in the workflow to define periodic boundaries. Right-click on the Generate the Surface Mesh task, insert New Task and click on Set up Periodic Boundaries. This task can also be added before generating the surface mesh, but with some limitations. In this task, the Type menu lets you select between the two types of periodicities, rotational and translational. In our case, we will use rotational. Next, set the method to Automatic Pick Both Sides. That lets you select the two periodic boundaries and automatically detects the angle and axis of rotation. However, user can also set the method to Manual Pick Reference Side, which instead requires specifying the inputs for rotation relative to the selected boundary. From the list of labels, select the two opposite sides of the sector, that is the side 1 and the side 2. Keep the Remesh Asymmetric Mesh Boundaries option to Auto, that would let the software choose whether to remesh the boundaries or not. Note that for the manual method, the Auto option is not available. Execute the task to confirm the operations. In the Describe Geometry, for the geometry type, select the second option as the imported geometry consists of only fluid regions. Choose Yes to change the fluid boundary type from wall to internal, which will allow the fluid to flow across the regions. As shear topology operation has been performed at the CAD stage, there is no need to perform here in the meshing stage. Click on Describe Geometry to execute the task. In the Update Boundaries task, you will see that the two sides used for periodic boundaries are set as periodic and shadow. Upon import of the mesh in Fluent Solver, the two sides will be merged into a single periodic boundary condition. Based on the label names defined during the CAD phase, appropriate boundary type have been automatically assigned to the rest of the boundaries. Click on Update Boundaries to move to the Update Regions task. Here, make sure that both the regions have been assigned with fluid region type and then execute the task. Now we will add boundary layers on the walls of the fan and the enclosure to accurately capture the near wall fluid behavior. Set the number of layers to 5 and make sure to set the fluid regions option in the Add In field and only walls option in the Grow On field. Hit the Add Boundary Layers button to execute the task and move to the Generate the Volume Mesh task. Here, for our demo, let's keep all the inputs at their default values and generate the volume mesh using the Polyhedra Fill With method. The minimum quality of this cell is well above the recommended value of 0.1. With that, we have come to the end of our workshop.